Okay, let's start the chapter, not chapter 5, the lecture 5. We're going to talk about the gas. The property of gas is it can change size. You can actually compress it or expand it. So it's the size can be changed. That's different from the solid and liquid. It's very difficult to change the solid and the size of the solid, size of the liquid. Those are difficult to change. But gas, it's easy. Gas is also low density, and then it fills the containers very easily, and it is homogeneous. So what I meant by homogeneous, it's just like a milk. The homogeneous milk, the taste at the top of the gallon is the gallon chug. It's a top part and the bottom part. They have exactly the same taste, right? The homogeneous mixture for the gas literally means that if you have the container look like this, maybe a strange shape container, right? And then that if I actually pick the small region of that, and in here I have 3 A molecules and then 2 B molecules, right? And then that I pick the different regions, maybe somewhere around here with a different shape, but the area is pretty much the same, or the volume is pretty much the same here. Then that I'm gonna find the same number of molecules in these regions too. So the volume here and the volume there is exactly the same. Then that I have I will find exactly the same molecules, same number of molecules in the same ratios. That's what I meant by the homogeneous. All right, so that's good enough. Then and it obeys, this one is important, ideal gas law, the PV equal nRT. So let me just explain that one, because you are going to solve these equations over and over and over again. So this one right here is a pressure, and the usually unit that I use is ATM. That's the pressure. And then that's the volume. And I use a liter here. And then N is for the number of moles. And then R is a gas constant, which is a 0.082. Oops. And then temperature, we use Kelvin. So anytime that you deal with the problems, I always change the pressure to ATM, and then I change the volume to the liters. If it's given in the milliliters, I'm going to change that to the liter. And then if it's the temperature is given as the Celsius, I'm going to change it to the Kelvin. And then I use the 0.082. Every single time that if you use all these units here, then you're always going to use this gas constant to be 0.082. So keep that in mind. Then side stories about this pressure. I don't know how many of you actually took the physics, but pressure is actually equal to force divided by areas. And force is actually given by, in the standard unit, it's 1 Newton. Mass times meter, distance, divided by the second square. So if I actually divide these things by the area, which is in the standard unit, it's meter square, right? Then the pressure unit is actually kilogram meter second square divided by meter square, which is actually kilogram divided by meter second squared. So that strange unit is the unit of the pressure. or you can actually write as 1 Newton per meter square. And all of these guys, I'm going to give you the conversion formulas for the pressures, but or the unit conversion stuff. I'm going to give you the conversion factors, but for the ACS exam, I sometimes remember that 1 ATM is actually equal to 760 millimeter Hg or 760 torr. I just happen to remember these things because I've been doing this for quite a long time. And then the 100 kilopascal is just about 1 ATM, and 1 bar is close to 1 ATM. Those are the stuff that I remember. Alright, so let me just talk about this PB collinearity again. I'm going to talk about just the unit here. So pressure is given by this one, right? And then the volume is actually given by this one. So this one right here, the left hand side is actually Newton meter, right? That these guys, let me just try to change that one. That wasn't a good. These two is in the Newton meter, right? Because the meter square is going to cancel two of those guys, right? So Newton meters. But Newton was what? It's a kilogram meter second square, right? Multiply by meter. What does it give? It's a kilogram meter squared second square. That's same as a joule here. So on both sides, these guys have the unit of the joule. So it's actually, we are equating the energy and energy here, because the one side is having the unit of joule, the other side has to have the unit of joule, right? So nRT is also the unit of the energies. Now, so what does that mean? What is the dimensions of the R here? So we know that it's going to end up having the unit of joule, and N is actually the number of mole. I'm going to put the mole here, and then the R is something that we don't know, and then the T is a Kelvin, right? So what's the stuff that has to go in here? That's actually the joule mole Kelvin, right? That's the unit of R here. Not important, but sometimes it might come in handy. Not for this class, by the way, but it's maybe later on in your life that you may take the upper division class, then those stuff might actually come in handy. Then, you might actually notice that I actually listed that R to be 8.31 in this standard unit form. That one is energy related to R. So whenever you're talking about energy of the gas, you tend to use this one. But whenever you're actually talking about ideal gas equations and you're talking about the ATM stuff, then R is actually 0.082. So those are the two type of R that I want you to remember. So for the first half of this lecture 5, we are going to be concentrating on this, using this guy right here. The unit is this. And then maybe the second half of the lecture 5, we're going to come back to this 8.314. So to summarize, we use ATM, volume, use liter, T, use K. And then R, we're good enough to use 0.082 all the time. Alright, so let's just try to solve some of the typical questions here. So here is a typical questions. For ideal gas, calculate the pressure of gas if 0.1 mole occupies 100 milliliters at this temperature right here. So PV equal nRT, right? Now the volume right here is actually 0.1, right? Oops, let me just try it. That was ugly stuff. 0.1, right? And then we're trying to solve for this one right here. And n is 0.12. And then we are going to use the 0.082, and then the temperatures, we're going to have to convert this Celsius to Kelvins. So we're going to add the 26.85 plus 2200, this number, right? So that goes in here. So yeah, if you actually plug all these things into this equations, you can actually solve for this one. I just say that this problem is already solved. Okay, let's do the next problem. The steel cylinder with the volume of this 68 liters contains O2 at pressure of that at this pressure, this temperature. What is the volume of gas at STP? This is standard temperature and pressure. Now the standard temperature and pressure is not what you think it is. The STP is actually absolute pressure of the exactly 10 to the power of 5 Pascal. Remember, it's a 100 kilopascal, right? So yeah, this is probably close enough for the 1 atm. So we're just gonna say that the pressure is STP. Pressure is approximately 1 atm. So 1 atm is good enough. I think that's probably good for the ACS quiz too. So that's fine. Then and temperature, that's a big one. Temperature is actually 0 degrees Celsius, okay, not the 25 degrees Celsius. So that one right here is 273.15 Kelvin. Okay, that's pretty much all you need to know. So let's just use some PV equal nRT. So we're gonna have to convert this this number into the ATM, right? Remember that 100 kilopascal is approximately 1 ATM, and that one right there is actually close to 159 ATM. And then the volume is 68. We're gonna use the 68 liters. That's fine, no change needed. And then temperature right here, if I add 273 on this one, then I get like a 296.15, and then R is 0.082. Then we get the value of N here, whatever the number it is. You can actually calculate this N, right? And then you want to use that N for the next one. So I'm gonna write the new PV equal nRT. For this particular time, it's 273.15. Pressure is 1. Volume, we don't know what it is. That's the stuff that we are going to solve. And then that N right here is gonna go in right here, and then R right here is at 0.082. All right, so all you have to do is that you just need to solve this one again. Once you use this one, you can actually get this number, and then plug that things in here, then you can actually get this number. So all of these problems are solved. Now actually that you just have to do it by yourself, right, using the calculators. So the other typical problem is that sometimes that it's not, I'm not going to give you all the pressure, volume, number of mole, and then temperatures, right? But sometimes that I might give you the density and mass. Then what happens? The density, remember the density is the mass divided by volume, right? Then if the density is given, right, and if I also give mass too, then you can actually solve for the volume, right? That's the volume is actually equal to mass divided by density, right? And then you just use that volume into that one, right here. Then you can actually solve the PV equal nRT. And a little bit more complicated problem is that I only give you the densities. What's going to happen here? That one right there is, let's just start out with the PV equal nRT. And then we're going to get the number densities. So that's, all I did is just rearrange this equation right here, right? And then I multiply both sides by the molecular weight, and remember this number of mole times the molecular weight is actually the mass, right? So this one right here is mass divided by volume, right? That's equal to mass divided by volume. That's basically the densities, right? So the density is actually equal to molecular weight times pressure divided by RT. So if you're not good with algebras, you might want to actually remember this formula, that formula right here. Density is the molecular weight times the pressure divided by RT. Oh, that important portions, that right? Just whenever you're solving for this type of stuff, always use parentheses when you divide something, right? That's the warning for those of you who use the calculators, because every time you forget to use the parentheses, you might actually find out that your number may be completely wrong, and I can't give you the full credit for that. So yeah, just be careful. All right, so that was the case one for the ideal gas. And then the next one is that sometimes not all the informations are given. So for these type of problems, you just have to be good at reading the problem here. So let me just try to read this problem right here. Consider you have closed balloon. Balloon can actually change size, right? And initially contains 2 liters of air at 298 K. So initially it started out with 2 liters of air at 298 K. Stretch the volume, stretch the container to make the volume twice as large. So now that the volume is 4 liters, what's happening there? For this particular case, I assume that the pressure, not pressure, that the temperature is constant, right? Temperature is constant, volume is changing. What's happening here? Number of mole is not changing because there is no mentioning about the chemical reactions, right? So no reactions, constant T, but not fixed volume. So PV equal NRT, that's where I start out. And then I am going to shift everything to the right for the one that's being the constant. So N is constant, right? N is not changing. R is not changing. It's not never going to change. And then the temperature is constant too. That means that temperature is not changing. I just guess that's what's happening here from reading these programs. Then anytime you look at it, let's just say that I look at the system at the very first time, then the pressure times volume is equal to this NRT. And then maybe 2 hours later, I'm going to look at exactly the same stuff, maybe in a different pressure and volume. That's also equal to this NRT, right? Because NRT never changes. Then what's happening here? The P1, B1 is actually equal to P2, B2. That's what's happening here. P1, B1 is equal to NRT, and NRT never changes. And that's equal to P2, B2, right? So the condition 1, under condition 1, number 1, and the condition number 2, the pressure times volume is equal to pressure times volume under different conditions. So you can actually solve this problem now. So it starts out with a 2 liters, right? And then you want to change this to the 4 liter. The pressure right here, you can actually calculate this pressure. Maybe you don't, but you have this pressure, right? And then what's going to happen here? We actually had this 2P1 is actually equal to 4P1, right? P2, sorry. That's because that the volume changed from 2 liters to 4 liters, right? Then the pressure 2 has to be half of the pressure 1, right? So that's pretty much how you solve this problem. So pressure is going to decrease to half the value of the original pressures. Ask me questions in the class if you actually have hard time following what I'm saying here. Alright, let's do the question number 2. Consider you have a closed balloon. Again, that balloon is going to change the size. Contains 2 liters of air, 298 K, at constant pressure. So this time around, it's a constant pressure. But now that the temperature is changing. So I'm going to start again. PV equal NRT. And then I'm going to move every constant to the right hand side of the equations. That's n, by the way, not 11. Okay, so move constant to the right. The pressure is constant, right? But temperature is not. So B divided by T is NR divided by P. Right? All of these guys are constant now. That means that under condition 1 or the condition 2, the center value doesn't change, right? So you get this B1 divided by T1 is equal to B2 divided by T2. So let me just try to figure out what this 2 liters, 298K, that was under the condition 1. And then this one right here is a 200K. Then you can actually solve for that number, right? So that's how you solve this type of problem. So start out with PV equal NRT, move every constant to the right, and everything else goes to the left, and then condition 1 and condition 2. That has to be unchanged. Hope you get the patterns now. Now, this time around, the following reaction happens. When the reaction happens, the number of mole of gas may actually change. So when I actually look at this one right here, 3 mole of gas becoming 2 mole of gas. And then initially it had a 3-liter balloon, right? Under constant pressure and temperature. What is the volume of the balloon? So again, PV equal nRT. Pressure and temperature is constant, right? So I'm going to move the pressure on this side. And then N is changing, so that, right? And then all of these guys are constant, so you can actually change this one in a condition 1 and condition 2. So yeah, it's B1 N1 is equal to B2 N2. Before the reaction, I had a 3 mole of gas here, right? 1, 2, and 3. And then after the reaction, I had only 2. So this one is going to be 2. And then that one right here is a 3 liter. What is this number? It's easy to figure it out. So it's probably good enough to actually say that this problem is solved. Alright, let's do the next problem. So now I have this following reaction right here. And what's being constant? Constant volume, constant temperature. So this time around it's a constant volume, constant temperature. N is changing. So PV equal nRT. N is changing. So V divide constant volume, right? Okay. So P divided by N is equal to RT over V, then P over N, 1, 1, 2, 2. So P1 over N1 is equal to P2 over N2. So 1, I had a 3 mole, 2 mole, and then P1 was no, the P1 is actually not given. What is the final pressure? For this particular case, that the P1, you can actually calculate this one, right? PV equal nRT. So I had a mixture of 3 mole at initially. It's 0.082. Volume is 1 liter. And then temperature is 298. Then you can actually get this one, this number right here, right? And whatever the number you get is you're gonna plug that things in here. And then you can actually get the final pressure here. And I think that's good enough. I think that's probably good enough for the first part of the lecture 5.